morning and welcome to Health Risks. I'm pleased to introduce our next three speakers. First two regarding the health risk of arsenic, and followed up finally with microcystin. I'm sure these will all be very exciting presentations. So let's begin right away, and then we will ask the presenters questions at the end of the three presentations to allow a little bit more time to get those questions to me. And let's start with Marco Barajas and Erin Hull. Take it away.
Barajas, and I'll be co-presenting with Erin Hull. Other authors made it possible is James Gawel, Kenneth Burkart, Ricky Pendergrass from UW Tacoma, and Samantha Fung, Pamela Barrett, Rebecca Neumann, and Julian Olden from UW Seattle. Also, we have Brian Jackson from Dartmouth College. This presentation is on human health risk from consumption of aquatic species in arsenic-contaminated shallow urban lakes. The Ozarko copper smelter was located in western Washington and operated for nearly a century. The smelter was decommissioned in the 1980s and demolished in the early 1990s. The plumes from the smelter had deposited arsenic and led across the south-central Puget Sound region, which raised health concerns for people that live in North Tacoma and Russian area, which became a Superfund site. Past studies done by Gawel and others have reported high levels of arsenic in sediments from lakes in the affected area. Here we can see two pictures of the Ozarko's copper smelter, and on the bottom right, you can see the arsenic concentrations from the plumes downwind from the Ozarko smelter. After examining several lakes for arsenic contamination, the study focused on two of the most contaminated lakes found from the research led by Gawel in 2014. Both Lake Killarney and Angle Lake have 200 parts per million of arsenic in the sediments. Angle Lake is a deep lake of around 14 meters at max depth, Lake Killarney being a shallow lake of around 4 meters max depth. The hypolunians in both of these lakes experience anoxia in the summertime. Furthermore, Angle Lake will stratify through the season, whereas Lake Killarney undergoes frequent mixing events, which is very typical in most of the shallow lakes. In both lakes, arsenic is released from the sediments during periods of anoxia. In Angle Lake, the arsenic remains in the anoxic hypolunium for the most part, and separated from the organisms residing in the oxic epilunium of the lake. In Lake Killarney, on the other hand, frequent mixing events causes the release of arsenic to mix in the oxic water column where the majority of the organisms reside. Evidence of this hypothesis is that phytoplankton arsenic concentrations in Lake Killarney is around 970 parts per million, whereas Angle Lake has a max of 170 parts per million. With such high levels of arsenic at the base of the food chain, we wonder, how does this translate to higher trophic levels in the food web? And ultimately, what are the implications for human health? Arsenic, without a doubt, is toxic to humans and other biota. In addition to being carcinogen, even at low levels of long-term exposure to arsenic has been related to an increased incidence of diabetes, hypertension, decrease of male fertility and other reproductive tissues, kidney and bladder disorders, cardiovascular disease, and respiratory problems. In 2019, the Agency of Toxic Substance and Disease Registry listed arsenic as number 1 on the substance priority list. So we decided to quantify arsenic concentrations in the edible tissues of 3 organisms commonly found in the lakes of the region and known to be consumed by humans. These species are snails, crayfish, and fish. We also assess the human health risk from consuming these organisms later on. The organisms collected were from lakes that have been studied from the past. These lakes have a range of arsenic concentrations in sediments and different mixing regimes. 3 lakes are considered shallow of less than 8 meters and therefore polymictic and represent a gradient of arsenic contamination. Lake Killarney being the highest arsenic in the sediment, followed by Steel Lake having moderate and Bonnie Lake having the lowest amount or considered the reference site. 2 lakes are considered deep, having more than 10 meters max depth. Angle Lake being the highest arsenic amount, followed by Pine Lake being the low arsenic or the reference site. Bonnie Lake didn't have any crayfish, so we decided to use Pine Lake as a low or reference site to collect the crayfish from. The next 3 slides show the species caught for the project. All species are non-native except for the signal crayfish. We analyzed the edible tissues for total arsenic, and a subset of samples were sent to Dartmouth for arsenic speciation. Each symbol indicates a lake, and the open symbol signifies that it is a deep and seasonally stratified lake. The closed symbols indicate shallow polymictic lakes. Arsenic in the snail tissue increases as the background arsenic in the sediment increases as well, Lake Killarney being significantly higher than the other 3 lakes. The figure to the left has a better correlation between arsenic in the snail tissue and arsenic in the shallow sediments, as opposed to arsenic in the deeper sediments shown in the right figure. Arsenic concentrations follows the same trend as the snails, Pine being the lowest and Killarney being the highest. Moreover, there are higher arsenic concentration in the pancreas as opposed to the tail meat for the crayfish. Once again, Killarney is significantly higher than Pine and Steel. The reason why we analyze the hepatopancreas is that it is also a food source known as the crayfish butter. Arsenic concentration is significantly higher in Killarney, followed by Steel Lake. Both Bonnie and Angle Lake have the same concentration in fish muscle tissue despite the difference in sediment concentration. Angle Lake having 35 parts per million and Bonnie Lake having 10 parts per million. Fish spend most of their time in oxic water columns where arsenic concentration in both Angle and Bonnie are less than 2 parts per million. The summary table shows the overall transfer of arsenic from sediment to primary producers down to the higher trophic levels. The amount of arsenic in each species correlates to the sediment concentrations. Arsenic being the highest in Killarney, followed by Steel, Angle, and Bonnie Lake. You will notice that phytoplankton soaks up more arsenic than the background sediment concentrations, except for Bonnie and Angle. Zooplanktons then eat phytoplanktons and are then consumed by snails or fish in the process of filter feeding. Crayfish, on the other hand, will eat whatever they can get their hands on. Arsenic in fish muscle tissues are less than 1 part per million. Unfortunately, there is no data for crayfish in Angle and Bonnie, as there aren't any reports of crayfish spawning in these lakes. And now I will pass it on to Erin Hull, and she will talk about arsenic speciation and the health assessment.
Thanks, Marco. So here we have a bar graph of the percent inorganic and organic arsenic in organisms from Steel and Killarney lakes. We're interested in these ratios because the risk assessment model only takes inorganic arsenic into account. This is because inorganic arsenic is much more toxic to humans than organic forms of arsenic. We included phytoplankton here to explain why snails have such a high percentage of inorganic arsenic. Phytoplankton and periphyton are the main component of a snail's diet and mostly comprised of inorganic arsenic, whereas crayfish and fish have a more varied diet and are positioned a bit higher up in the food web. This trend you see here is expected because arsenic is biotransformed with each trophic transfer along the food chain. Fish in particular are known to contain high amounts of ASB, which is an organic arsenic compound that is relatively non-toxic to humans and other biota. To assess the human health risk of consuming each type of organism, we applied the average percentage of inorganic arsenic in organisms from Steel and Killarney to all lakes in the study. We focused on 3 different adult, so 18 years and older, consumption rates used by the EPA, and these are all for the consumption of freshwater and estuarine organisms only. We have the mean consumption rate representing the general U.S. population. This category has 2 slightly different consumption rates, shellfish, which are the snails and crayfish in the study, at 3.27 grams per day, and finfish at 4.23 grams per day. Then we have the 90th percentile consumption rate, which is recommended by the EPA because it is more protective of high consuming populations at 17.5 grams per day, and this rate combines both finfish and shellfish. And finally, we have the 99th percentile consumption rate, which is an average rate based off of subsistence fishing populations in the U.S. at 142.4 grams per day, again combining shellfish and finfish. So results for the non-cancer health risks are presented as a dosage based on the amount of inorganic arsenic in edible tissues. Non-cancer health risks may include skin disorders, reproductive issues, developmental and cognitive disruptions, complications of urinary and gastrointestinal systems, diabetes, and cardiovascular diseases, to name a few. So for the 99th percentile of consumers, we found that snails from all lakes and Killarney crayfish are above the EPA's chronic oral reference dose for non-cancer effects, which is 3 × 10⁻⁴ micrograms of inorganic arsenic per gram, highlighted in yellow, and basically means that non-cancerous adverse health effects are possible. And Killarney snails are also above the reference dose for the 90th percentile of consumers. Here we see the cancer risk part of the assessment. Results for cancer risk are a little different than the non-cancer risk dosage. So a value of 1 × 10⁻⁵ or E-5 means 1 additional cancer occurrence in 100,000 people. Here we're considering an increased cancer risk to be above 10⁻⁵ based on recommendations by the EPA. Results that exceed that limit are highlighted in yellow. Results highlighted in orange represent an even higher increased cancer risk, exceeding 1 additional cancer occurrence in 10,000 individuals, or 10⁻⁴. The most concerning results are those with an increased cancer risk above 10⁻�3, or 1 additional cancer occurrence in just 1,000 individuals, highlighted in red. Snails from Angle, Steele, and Killarney at the 99th percentile consumption rate are flagged at that level, with Killarney snails resulting in over 4 additional cancer occurrences in 1,000 people. Overall, the cancer risk from consuming each type of organism decreases with increasing trophic level. This is partly due to the percentage of inorganic arsenic, which also decreases with increasing trophic level. Furthermore, shallow lakes with moderate or high arsenic contamination, Steele and Killarney, consistently have the highest cancer risk for each type of organism. Maximum arsenic concentrations in Angle Lake sediments are just as high as Killarney, yet its cancer risk levels are still lower than both Steele and Killarney. Another takeaway from these results is that unregulated consumption of Chinese mystery snails could be problematic. Even snails from Bonny Lake, which is the shallow lake with background or low levels of arsenic contamination, results in an increased cancer risk using the EPA's default consumption rate. So putting these consumption rates into perspective, the EPA recommended 90th percentile consumption rate of 17.5 grams per day, which includes both shellfish and finfish, is equivalent to consuming about 3 snails or crayfish a day. And that's assuming you only ate that one type of organism and no other type of shellfish or finfish. That's based on average uncooked weight of snails and crayfish collected in our study. Now, if you're thinking some of these shellfish consumption rates seem high, we looked at consumption rates for just snails or crayfish taken from international studies with the assumption that immigrant populations may maintain similar dietary practices. The estimated mean consumption rate of snails alone for the Lake Taihu region in China is 20 grams per day. The mean consumption rate for crayfish, based on a survey also from China, is 10 grams per day, with 118 grams per day for the 99th percentile of consumers. So the low and high-end consumption rates we use serve as a realistic bracketing of the potential risk to you as consumers, including the most vulnerable population of subsistence fishers. That being said, there's still controversy over whether rates are truly protecting everyone. For example, the highest reported fish consumption rate in Washington state is 865 grams per day for the Spokane tribe. This is almost 50 times higher than the EPA recommended rate. So, in conclusion, the dynamics of shallow polymictic lakes can result in greater arsenic bioavailability compared to deeper, seasonally stratified lakes, and therefore greater human exposure and health risk. We recommend that monitoring the extent of arsenic contamination include littoral sediment sampling, as concentration in shallow zones may be a better indicator of the potential uptake into organisms compared to conditions in the deeper areas of lakes. And finally, we suggest that regional agencies consider regulating the consumption of aquatic species that are especially susceptible to the uptake of arsenic, like the Chinese mystery snail. So thank you all for giving us your attention, and to the WALPA organizers for making this virtual conference happen. In addition to all our amazing co-authors, we'd like to give special thanks to Lenford O'Garl for guidance with the risk assessment, Becca Styling, Noelle Hogan, and Suji Kim for their help in sample collection and processing, and to the NIEHS Superfund Research Program for funding this study.
Thank you very much, Marco and Erin. That was fascinating. No escargot for me. Anyway, we're moving on to Samantha Fung. She's going to kind of carry on the same theme here. So take it away, Samantha.
All right, so I think, can you guys hear me okay? Great, okay. So my name is Samantha Fung. I'm a graduate student at UW, and I'm gonna follow up Erin and Marco's wonderful talk and look at some of the seasonal patterns of mixing and arsenic concentrations in Lake Killarney, our small study system. So next slide, please. So first, I'd like to acknowledge the Native people of the land where I work and conduct research. The land occupied by the University of Washington, indicated by the top star, and our study lakes, indicated by the bottom 4 stars, was originally inhabited by the Coast Salish, Suquamish, Duwamish, Puyallup, and Muckleshoot nations. Next slide. So Erin and Marco just did a great job of introducing the study and discussing the human health risks that occur when arsenic ends up in the organisms we consume. However, we really need to understand the background mechanisms that lead to high amounts of bioaccumulation so that we are able to predict which contaminated systems are most at risk for having adverse human and ecosystem health impacts. In this talk, I'll focus on the physical and biogeochemical mechanisms that are involved in the pathways of arsenic transport in small lakes. I'll be using data from Lake Killarney, our small study system represented by the shallow lake in the left of the schematic. Just to review its characteristics, Lake Killarney has a max depth of 4 meters and is polymictic. As the schematic shows, arsenic is generally fixed in the bottom sediments of the lake. So imagine an arsenic molecule stuck to the sediment at the bottom of the lake. What pathways must this molecule go through to make its way from the sediment into an organism? Next slide. So first, it must be mobilized from the sediment into the pore waters surrounding the sediment. Next, it must diffuse from the sediment pore water into the hypolimnion, or the water right above the sediment water interface. Third, it must mix from the bottom water into the bulk oxic water that the organisms inhabit. Lastly, it must be taken in by primary producers and transferred through the food web. I'm going to focus on these first 3, so let's dive into mobilization. Next slide. So arsenic mobilization is a microbially mediated process that is dependent on both temperature and dissolved oxygen. I'm going to quickly talk about redox reactions, and hopefully I don't induce too many flashbacks to high school chemistry. So microbes living in the lake sediment consume and oxidize organic carbon as a food source. In oxic conditions, these microbes will couple the oxidation of carbon with the reduction of oxygen. However, when there's no oxygen, microbes next choose to reduce iron. Specifically, they reduce iron 3, a solid form of iron, to iron 2, a dissolved form. As a result of the dissolution of iron, arsenic is released and transformed to arsenic 5, a solid form, to arsenic 3, a dissolved form. Once the arsenic is mobilized into the pore water, it undergoes passive diffusion. Can you click the next? Yeah, so it undergoes passive diffusion into the water right above the sediment water interface. Because both microbe activity and diffusion are processes greatly regulated by temperature, the release of arsenic from the sediment into the pore water and its diffusion into overlying waters are also temperature dependent. Okay, next slide. So Pamela Barrett, a postdoc who previously worked on this project, investigated this temperature effect in a lab study published last year. She incubated sediments from two of our study lakes, Algal and Killarney, which Marco and Erin previously mentioned. So the data indicated, the data shown in blue indicates soil incubated at 10 degrees Celsius, and the data shown in red indicates soil incubated at 20 degrees Celsius. As the plot shows, arsenic was not mobilized at 10 degrees Celsius in the lab, but it was mobilized at 20 degrees. So we know that arsenic mobilization begins somewhere between 10 and 20 degrees, but where is that threshold? Luckily, we have field data to help us hone in and answer this question. Next slide. So as part of our multi-year field study in Lake Killarney, we deployed passive pore water peepers at the sediment water interface for 2-week periods. The peepers hold sample vials, shown by the little circles here, above and below the sediment water interface. The vials are filled with tracer solution and covered by a membrane filter that allows the fluid inside to equilibrate with the fluid outside and gives us estimates of arsenic concentrations in the pore water surrounding the sediment and in the hypolimnion, or the water right above the sediment water interface. Using these concentrations in conjunction with measurements of sediment temperature, we can look at the relationship between sediment temperature and arsenic mobilization in the field. So click. Okay, so these plots show sediment temperature versus arsenic concentration from 13 different peeper deployments over a 2-year period. Each dot represents a peeper deployment where I average the sediment temperature over the 2 weeks. So to look at the temperature effect on mobilization, I have the sediment temperature plotted against the mean arsenic in the pore water on the left. And then to look at the temperature effect on diffusion, I have the sediment temperature plotted against the mean arsenic above the sediment water interface on the right. So there appears to be a temperature threshold for both of these mechanisms, which makes sense because we know both microbe activity and diffusion are temperature regulated processes. So below the threshold, and you can click one more time. So below the threshold, which is about 13 degrees Celsius, we don't see very much arsenic mobilization or diffusion. Above the threshold, we see a potential for high arsenic, but some variability in the response. So the takeaway here is that the sediment temperature must be above a threshold of 13 degrees Celsius for arsenic to be released into the sediment and diffused into the overlying water. Okay, so this data is zoomed in right at the sediment water interface. Now let's zoom out and look at what's happening in the whole water column over time. So next slide, thanks. So in the top panel, now I'm showing a time series of sediment temperature where the blue shading indicates periods where the temperature is above our identified threshold. In the bottom panel, we have profiles of arsenic throughout the whole water column with a depth of 0 indicating the water surface and a depth of 3.5 meters indicating the lake bed. So indeed, when the sediment temperature is below our threshold, we see very little arsenic in the water column, which is in line with our conclusions from the last slide. However, during periods when the sediment temperature is above the threshold, we see a variety of patterns. During some periods, there's a gradient of concentration with high levels near the bed and lower levels near the surface. During other periods, we see a more uniform distribution of arsenic. So to bring this back to our central motivation, we really want to understand when and why arsenic concentrations are elevated in the upper waters, because this leads to uptake into the lake organisms. Okay, so now that we can see the whole time series, let's zoom in again to a couple different of these time periods and investigate what's controlling the different patterns. So next slide. Okay, so let's start by looking at the month of August in 2018. During this period, we see a gradient of arsenic, And to look at why this is the case, we need to look at the physical lake mixing and the DO patterns during this period of time. Next slide. Okay, so this slide has a lot of information, but I'm going to break it down. So the left two panels, the left two plots, are showing time series for the month of August. On the top left, we have dTdz, or the change in temperature over the lake depth. This is a measure of stratification. When dTdz is 0, shown by the dashed line on the bottom of the plot, there's no change in temperature over the lake depth, indicating a fully mixed system. A positive dTdz indicates that the lake is stratified, with strength of stratification increasing with a greater dTdz. On the bottom left, we have sediment temperature as the blue line, the sediment temperature threshold shown by the dashed line, and then the bottom water DO in orange. Lastly, on the right, I have plotted the same arsenic profile we saw on the last slide in the red box, now just with arsenic concentration on the x-axis rather than shown in color. So it's just a line plot now instead of a color plot. And then the blue triangle is indicating the day when this profile was taken. Yeah, okay, thanks. So I'm going to spend a bit of time talking about this measure of stratification before fitting it in with the other two plots. So you may notice that there's a diurnal pattern. During the day, solar heating causes stratification to strengthen. However, in the evening, the air cools the water surface, causing convective mixing and a subsequent weakening of the stratification. Full mixing occurs when the water surface cools below the temperature of the rest of the lake, and this surface water sinks due to its increased density. You can observe this happening when dTdz briefly dips below 0, indicating an inverted temperature profile and a complete mixing event. So the patterns in nighttime convective cooling and mixing are extremely important because they control the distribution of dissolved oxygen and arsenic throughout the water column. Okay, so now connecting to the other two plots, looking at the first and second nights of August, we see two full mixing events where dTdz reaches 0. Because this is mixing oxygen-rich surface waters into the bottom hypolimnion, we see simultaneous spikes in the bottom water DO. For the next week after this, the lake water column stays stably stratified, and there's a consistent decrease in the bottom water DO. For the rest of August, we see periods of stable stratification interspersed with occasional mixing events. This pattern produces the arsenic gradient we see in this August 16th profile. Large amounts of arsenic are being loaded into the bottom waters when the lake is stratified. During occasional mixing events, some of this arsenic is mixed into the upper waters. Because these mixing events are infrequent, the arsenic is allowed to build up in the hypolimnion, leading to our observation of high bottom water concentrations and lower surface water concentrations. Okay, next slide. Awesome, so let's hop 1 month forward and look at September of 2018. Yeah, so now we're looking at September of 2018. So the temperature of the sediment is still above our threshold, but now we see a uniform distribution of arsenic. Okay, now you can go to the next slide. Cool, thanks. So looking at dTdz again, we see that the lake is fully overturning almost every night. As a result, the bottom water DO remains relatively high, and the arsenic is distributed evenly throughout the water column, as seen in this profile taken on September 10th. Okay, so now that we've examined 2 month-long periods, let's zoom back out and look at how sediment temperature and stratification control the arsenic concentration seasonally. Next slide. Awesome. So again, we have our sediment temperature in the top panel and stratification in the middle panel. And now the bottom panel is showing time series of arsenic concentrations in the top and bottom of the water column, with the top being in blue and the bottom being in orange. Okay, so in the wintertime, click once. So in the wintertime, sediment temperature remains below our threshold. Consequently, little or no arsenic is being mobilized from the sediment into the pore waters. Although the lake has a variety of mixing patterns during this time and is generally fully mixed, the top and bottom water column concentrations is negligible as there is no arsenic being loaded into the system. From late spring to early summer, so late spring to early summer, the sediment temperature is now above our threshold, and the water column undergoes periods of stratification with occasional mixing, like we saw in August. So during these months, we see very high bottom water concentrations and lower but still elevated upper water concentrations. Click one more time. So lastly, in the late summer and early fall, sediment temperature is above our threshold, but the water column mixes nightly. During this period, the top and bottom water arsenic concentrations converge. Okay, next slide. So our three main takeaways from the study are first, the release of arsenic from the sediments into the lake water is regulated by temperature. And specifically, arsenic mobilization from the sediment and diffusion from the pore water into overlying waters both exhibit a temperature threshold behavior with a threshold around 13 degrees Celsius. Second, in late spring to early summer, periods of stratification cause arsenic buildup at the sediment-water interface, and episodic mixing transfers arsenic into the lake epilimnion. These mechanisms cause a gradient of arsenic throughout the water column. Lastly, during summer and early fall, convection-driven diel or diurnal overturning distributes arsenic homogeneously throughout the full water column. So hopefully I've convinced you guys that in order to predict when arsenic contamination will overlap with biota, we need to understand the mixing mechanisms and how patterns of mixing interact with lake chemistry. I've just been watching all the other presentations and thinking about how lake mixing is so widely useful in other internal loading scenarios. So for example, with internal loading of phosphorus, which is controlled by the same mechanisms as arsenic mobilization, if we can predict when the lake will mix and when anoxia will form, we can time our treatments of alum or bubbling for when anoxia and phosphorus release is the highest. Similarly, if we are trying to remediate a lake for arsenic with the cool algal scrubbers that Ken and Sarah presented yesterday, we can plan to maximize flow when through the scrubber when the arsenic concentrations in the lake are the highest. Okay, next slide. So I just wanted to thank all of my wonderful co-authors and the field team, and of course, NIEHS for providing the funding. And that's it.
Well, thank you very much, Samantha. That was wonderful. Well, we're going to get to questions later. I have to wait. So we're going to move on to our last presenter, and that's Mr. Tim Clark from King County. Welcome back, Tim. Let's hear what you have to say about your Bayesian model. Yeah.
Toxic algae blooms are a major concern in King County's lakes. Every year, we have several lakes that close due to high levels of microcystin or anatoxin that exceed the state's recreational guidelines. This makes them of particular interest to our elected and appointed officials who are interested in managing our natural resources for both human health and ecological outcomes. And so they have come to us as in the Water and Land Resources Division to help expand on how different types of natural resource management activities can best manage harmful algal blooms as well as other endpoints. This effort is called the Water Quality Benefits Evaluation, and that's what I'll be talking about today. My name is Timothy Clark. I go by Clark, and I'll be talking about how King County is trying to connect actions to endpoints particularly focusing at swimming beaches. King County is in a time of planning. We have a really great collaborating effort around Clean Water and Healthy Habitat Initiative, which has the central tenet of making the right investments at the right time in the right places. This mantra is helping guide our Clean Water Plan, which is a long-term utility planning effort from the Wastewater Treatment Division, as well as this Combined Sewer Overflow Long-Term Control Plan update. And what the Water Quality Benefits Evaluation is trying to do is developing tools that are driven by the latest scientific information to provide evidence to decision makers on what types of actions can give us the biggest water quality benefit. So this tool will be used for both of those plans, as well as other strategic planning efforts for stormwater or land acquisition efforts. Because why do we improve water quality? We want to be able to eat shellfish and fish. We want to be able to swim safely without concern of. We want Chinook salmon to be recovering and abundant. We want orcas to be recovering. So what the Water Quality Benefits Evaluation is trying to do is be able to connect what actions we can have to these endpoints. And to do so, it is relying on 3 tools. The first of which is a pollutant loading model. So understanding where the pollutants are coming from on the landscape, whether it's combined sewer flows or stormwater runoff, and what kind of land uses are those pollutants coming from. Of major concern for lakes is phosphorus. And so that's one of the pollutants that's being modeled through this effort. And then and the second tool is a cost effectiveness model for best management practices and other actions. So looking at rain gardens and street sweeping and tree planting, how do these result in better water quality or decreased loading? And then actually, can we optimize a suite of those to be the most cost effective and give us the biggest bang for our buck for meeting our management goals? And then pulling that information from that loading model and optimization to see how those affect those endpoints I discussed earlier. How do those pollutants and other landscape factors impact the things that we care about? So I'm the causal model lead for swimming beaches, and swimming beaches are affected by 2 things: fecal contamination and toxic algae blooms. Today I'll be focusing on toxic algae blooms. Last year I talked a lot about poop, and so it's really exciting that I won't have to talk about poop at WALPA this year, other than this sentence. So kind of a big ask is that we need a general model for predicting algal toxins in over 50 lowland lakes as related to external phosphorus reduction. And we want that model to be simple, robust, easy to understand, and adaptable. We want to be able to put in new information and change it as we learn more about our systems, as well as we think about other types of actions that we might take on. So ultimately, we actually decided for all of these endpoints to be using a Bayesian network. And I'll talk more about a Bayesian network right now and what that is by providing an example. So a Bayesian network is really a causal web of conditional dependencies that capture the influence of parameters on one another using probabilities. So in this example, I'm asking, will I catch my bus? And so down here in purple is, will I catch my bus? And that's either yes or no. So I have 2 mutually exclusive states, and I can have 3 or 4, but as long as they're mutually exclusive. So whether I catch my bus or not is dependent on, do I leave the house on time? And does the bus arrive? And when does it arrive? Is it early, on time, or late? And then me leaving the house on time is in turn dependent on, do I oversleep? Or And is the bathroom available, or is my roommate hogging it? So within each of these parameters, these nodes, is a conditional probability table, which I pulled up here. So that outcome of leaving the house on time, yes or no, those two states. And then we have every iteration of oversleeping and bathroom availability. So in this first case, where I oversleep, but the bathroom is available, I think there's a 70% probability that I will leave the house on time. Whereas if I oversleep and my roommate is hogging the bathroom, there's only a 5% probability that I'm going to leave the house on time. And I generated probabilities for those other scenarios. And we can continue to go up the chain. So what causes me to oversleep? Well, it might be, or it's bad dreams. And what causes me to have bad dreams? It might be I have a presentation the next day and I'm stressed, or I ate ice cream before bed. And maybe I ate ice cream before bed because I had a presentation the next day and I was trying to do some self-care. So you can see how we're really kind of like, oh, I have a presentation the next day. That goes down this web into whether or not I catch my bus or not. So let's say I have a presentation tomorrow. It says yes. Oh, it becomes more likely that I'm going to eat some ice cream. It's fairly likely I'm going to have bad dreams then, 78% chance. About half chance that I'll oversleep. And with that, 56% chance I'll leave the house on time, and then I'll be able to catch my bus 57% of the time. So just knowing that I have a presentation tomorrow, I have a better chance than not of catching my bus tomorrow, but not by much. So maybe I should plan accordingly, or work from home forever. So that was just a brief example, and hopefully a kind of a fun example of a Bayesian network. So why were we interested in using Bayesian networks? Well, it allows us to use expert knowledge and data. So what I used in that model was my expert knowledge of living in my home and knowing when and where I'll be able to catch the bus. And then also I could use data. I could have structured notes for every day I've left, and was the bathroom being hogged, and developing all those cases. And then really it's just a frequency distribution of when this and this does this happen. So that's really great for us, so that we're able to handle areas where we have data gaps, but a lot of expert knowledge. Another area that is a strength for Bayesian networks is being able to handle uncertainty. By use of probabilities, it allows us for more of that squishiness of, well, I think A causes B, but not always, and even under all the right conditions, I don't think 100% that this is going to happen. So it allows us to understand that, not to allow us to really play with the knowledge that we don't know everything. And we can capture that really well through probabilities. So for building the algal toxin model, the first step was to find the experts, because this was going to be chiefly built on knowledge, because we don't have all the data necessary for all of King County's lakes. So the subject matters I was able to find, and boy, I was very pleased with the people I was able to bring on. We had Dr. Eugene Welch, retired professor of the University of Washington, Chris Knudsen from King County, our lake stewardship manager. He knows King County's lakes very intimately. Deborah Bouchard, senior limnologist with King County, and my boss, Dr. Ellen Priest, from Robertson Bryan down in California, previously out of Washington State University, and Dr. Joan Hardy, retired from the Washington State Department of Health, but doesn't seem like she retired. She never seems to stop working. So with these experts, we use the IDEA protocol, which is to present information to them, making sure we're all on the same place and trying to understand and remove any biases that might exist. And then asking them a question, allowing them to provide their answer, and then presenting those answers to all of those experts anonymously, and allowing time for discussion, for what's happening, and then and for experts to have a chance to explain themselves. And then they're able to make a second round of estimates, and then we move forward. So to go through this process, there was a lot of video conferences, and I sent out a lot of surveys. And because there's all these video conferences, I recorded them and watched them back later. I've got to find out how much I talk with my hands, which apparently is a lot and is very distracting. And I'm sorry, but this is how I talk. So I would often send them a survey. They would provide it. I would create a summary of their responses, and then I would present that through them in a video conference, and then they would do those responses. And so that's how we built the conceptual model, and we built all those conditional probability tables, that little table I showed previously. So this is sort of a general conceptual model for the algal toxin. We thought algal toxin down here at the bottom, influenced by the genotype of the algae that are present, as well as the amount of accumulation near the beach, how much of a scum is forming up. And that accumulation in turn was influenced by accumulation conditions, wind and macrophytes at that beach, and then how much cyanobacteria were lake-wide, what is the amount of abundance, which in turn was influenced by the nutrient availability, nitrogen and phosphorus, and then the environmental conditions, so temperature, light, grazing by zooplankton. So now I'm going to break that out a little more, specifically the environmental conditions and nutrients. So you're looking on the upper right with the environmental conditions. So we're looking at lake stability as measured through the Osgood index, mean summer temperature, the flushing rate, were large-bodied grazers present, and then light availability as influenced by sort of organic matter, that tannic color, and macrophyte coverage. For the nutrients, we were, based off discussion with experts, they really thought this was going to be driven by the N/P ratio, and so there's a place for that, and then also what the phosphorus is. And what we wanted to capture was, what do we expect the phosphorus to be after an external load reduction? And so we did that based off of different levels of internal load, like what fraction of the total load comes from internal sources. And so we looked at, so our post-treatment TP, so post-reduction, was estimated by our experts based off of what is the pre-treatment TP, and what is the amount of reduction of phosphorus from the external load, and what is the internal load fraction. And we allowed for a timeline. Is this the first 5 years after the reduction, or 5 to 10 years after reduction? And so now building out, and with all the CPTs in place, this is the fleshed out model. So what's really of interest to our decision makers is the knobs that we turn and the output. So they're going to be really interested in the external total phosphorus load reduction, as that affects the lake TP, and how does that affect the probability that in the summer we exceed the microcystin standard. So we are using microcystin here because that's the most common toxin we find in King County lakes. And it was thought that actions that would help manage microcystin would also help manage antitoxin. And for the purposes of the model, that was deemed to be sufficient. So we can actually set boundary conditions for a given lake. And I've done that here. And with these conditions, we have a 19.7% probability down the bottom of exceeding the toxin criterion. And then we can run a scenario in which we reduce the external load in the summer by 80%, which drops it down to 15.4%. And also I put this as 5 years after. So not a lot, really. And so that's actually a really important thing to be talking with our natural resource managers and decision makers, is that the external total phosphorus load management for a lot of our lakes is not going to be enough. We really have to look at both external load and internal load. So that's really important for our experts to know, or for our natural resource managers to know, is that external load and stormwater management and wastewater management for King County's lakes, as they currently are, will not likely be enough. This model is still under construction. Every time I meet with that team of experts, we come up with new ideas to how to make it better. And some of the structural changes that we're considering right now is moving from that cell density, cyanobacteria cell density, to either dropping it and plugging phosphorus directly into microcystin, as well as the environmental conditions, or using chlorophyll A, which, as we know, is an imperfect predictor, but being able to capture the uncertainty around that in this model will be very helpful. And that's the benefit of the Bayesian network. So this is still under construction, but I'd like to close with an invitation to you all. If you would like to review the beta model, which will be the next stage of the model, please contact me. I have really appreciated the input of my 5 immediate experts, and this model is their model. I have really just facilitated its production. And I really want to hear from all of you on how to make it better, and if what you see coming out of the model is believable and is aligned with your expectations. Yeah, so thank you for hearing me out today, and please let me know if you have any questions. Thanks.
Wow. Clark, that's pretty amazing stuff. Okay, well, we're time for some questions. We got a good 7 minutes or so. That's great. I'm going to start with Marco. What species of snail did you use? And I know you said something about the Chinese mystery snail and kind of how that species relates. And my question also is the uptake between differences between species, as well as the consumption differences between species.
Yeah, so the species is the Chinese mystery snails. It's very abundant on every single lake. The difference between the arsenic, we have not calculated that, but that's going to be on our next paper about how the arsenic transfers with up on the trophic level. And what was the last question again?
If there's a differences in consider different species and how their consumption rates are. If the human consumption rates vary between species. Yeah.
So the consumption rate between different species it's very controversial right now. We try our best to stay on the conservative side. As for the species itself, we only select the species that are available in our lakes because it's the more realistic model, or the most realistic way to represent the lakes here in South Puget Sound region.
Okay. And then secondly, for Erin, have you presented these results to the Department of Health? People are curious what the Department of Health thinks about the risks that you've observed.
Yeah, so we initially worked with the Department of Health, Glenford O'Garo. He kind of got us set up with the risk assessment model. And
I think in a few weeks, we do have an agency stakeholders meeting to kind of run through our results, get some input, and go from there. So before we publish anything, we definitely want to include those guys, get their input.
Great. Samantha, have you considered correlation between your temperature threshold and the sediment boundary layer dissolved oxygen to stratification strength, as you discussed? Other researchers have found low oxygen at the sediment water interface, and we're wondering if that was maybe missed in the 1 meter intervals that you measure, you collect the data.
Correlation between which two variables, the oxygen and stratification?
Yeah.
Yeah, that would definitely, I think it would match the correlation to arsenic release because arsenic is so closely tied to anoxic conditions, but that's definitely something I should plot up and look at, yeah.
So you related it to temperature. Did you measure dissolved oxygen continuously also, or just the temperature?
Yeah, I had the oxygen time series in those two, in the August and September zoomed in plots. I just haven't correlated the temperature and the oxygen.
Cool. All right. Okay, Clark, I got one for you. And that would be, did you look at pH in your model?
Certainly it was on the list of parameters that we were looking at in the early discussions around building that conceptual model for toxic algae blooms. Ultimately, it did not make the cut. There were a lot of different parameters that didn't make the cut. There are a lot of things that we believe can have some influence, but in terms of we really want to focus on the major drivers, especially around the areas that King County can have some influence on. And particularly around the WICB, the water quality benefits evaluation action, so stormwater management, which certainly can have effects on pH. But ultimately, through discussions with the experts, it was not included. But if during the beta model review, which whoever asked that question is certainly welcome to take part of, I already was contacted by Sally Abella, so come on and join the fun of the beta model review. And you can tell us all why this model is wrong and needs to have pH and how we can improve it. And so please join the discussion.
Okay. Well, thank you, Tim. I would say, Clark, that, well, there's a couple here. I don't know how much time we have, but I'm interested in the internal load. So the external load results kind of gave you what our limnologists know and told you that you've got to reduce internal load to affect algal biomass. So have you been used the model to evaluate changes in internal load?
I would love that as a next step in the model. For the goal of the model right now, we are looking at external load management as it relates to stormwater and wastewater management. So for the goal of this model to serve King County's purposes, we can't going deeply into internal load management through a Bayesian network seem beyond the scope. But as we know, and as this model showed, it's a very important piece for us to manage. And I think I'm really interested in having a discussion of whether or not internal load could be well estimated, and how alum treatment or dredging or other actions for managing internal loads can really be well modeled in terms of a Bayesian network, especially generalizing to a lake, because often that is so unique. And that's why we have lake management plans and very focused around how to manage internal loads. So I'd be interested to see if we can build a good general Bayesian network around internal loads in the future. Once we get into the second phase of this project, I think that might be a place of interest, but I really need to hear from the people who are running those budgets that they are interested in not doing just stormwater management, but potentially also using that money for internal load management. And I'll be like, okay,
let's build the model for it, and then we can prioritize around that. So not yet, but I hope so. Just have to make some good sales pitches.
Well, thank you. I do hope you win that sales pitch. That would be great for all of us.
It'd be great for business.
Yeah. But and then lastly, we don't have much time. It looks like time's up. But did you factor in, Tim, wind direction and wind speed in the environmental conditions?
Yeah, and so that's like a very generalized. Because we're looking at a certain beach within a lake, and so certainly wind conditions can vary by day. And so this is not like a daily model for accumulation, but there are general patterns in. Oh yeah, this is a cove in which we always get a lot of accumulation because the general wind patterns push it this way. So that allows for like the uncertainty around it. Like, yeah, we think there's this generally supportive conditions for having scum show up here at this beach. But we know that doesn't happen all the time. So that's captured, but like not on a daily time scale.
Great. Well, that's a great answer. Great answer from all of you. I really appreciate your time today. These were all great presentations. Give us a lot to think about. And I congratulate you in your research, and may you continue and teach us all great things in the future. Go WALPA, and we'll see you all at the next session, which starts at 11 o'clock in 10 minutes. So please come back and don't miss invasives management. Thank you.
Go WALPA.